Greetings. We are continuing with our discussions on steady flow equations. Remember, from first principles, we had said that dH was equals to V dP. How did you get that? We know that H, that's the enthalpy, is U plus PV. By using internal energy, P is pressure, V is volume. And so we said that dH is equals to du plus PdV plus V dP. Remember here, we have just simply used the product rule. We have used the product rule, that is du of V is equals to U dV plus V du. That's the identity we have used there. And from first law of thermodynamics, we know that du, from first law of thermodynamics, first law of thermodynamics, we know that du is equals to dq plus dw. And if you remember earlier discussions, we said that from Closius inequality, we know that ds is equal to dq over t, or we can say that tds is equals to dq. And for pressure volume work, dW is minus PdV. For PV work, dW is equals to minus PdV. So if you substitute that in expression for first law, therefore we have that du is equals to TdS minus PdV. So substituting this expression for du into the expression for change in enthalpy, we have dH is equals to TdS minus PdV plus PdV plus V dP. This, of course, remember, is du. So these two terms cancel. So we have dH is equals to TdS plus V dP. If we are talking of an isentropic process, remember, not isoentropic, isentropic process, that is the entropy is constant. We use that significantly in Rankine cycle. So for isentropic processes, ds is 0, therefore dH will be equal to V dP. This is an important expression, let's call it 1. So going back to our steady flow equations, recall going back to our steady flow equation, and I continue encouraging you to go through our earlier lectures systematically. From our steady flow equation, we know that we have dH plus dc squared over 2 plus gdz is equals to dq plus dw. This is representative of kinetic energy. This is representative of potential energy. And also, these are 0. So, if we assume there's no significant change from the datum level, we can assume this is also 0. So that we have dH plus dc squared over 2 is equals to 0. And so, let's call that expression number 2. So substituting 1 into 2, so if we substitute 1 into 2, expression 1 into 2, then this simplifies to V dP plus dc squared over 2 is equals to 0, or we have dc squared over 2 is equals to minus V dP. Let's call that expression number 3. Very simple. Just working with thermodynamic state functions and invoking very simple arithmetic processes, that's calculus. And so we have that particular quantity there. And if you recall, in our earlier lectures on steady flow equations, we said that from the continuity expression, where we have AC over V, 0, A is area, C is velocity, V is specific volume, if we take the logarithmic form of this expression, where I will use the identity log of x over y is equals to log x plus log y, and log of is log x minus log y, not plus, and log of xy is log x plus log y. That's using the simple logarithmic identity to sort out that, convert it to the logarithmic form. So into the logarithmic notation, we have log of a plus log of c minus log of v is equals to 0. If we differentiate this logarithmic form of the continuity expression on differentiation, we have dA over a plus dc over c minus dv over v is equals to 0. Remember, from the identity, if you integrate dx over x, that is the same as the integral of d ln x, which is ln x plus c. That's a very simple identity in integral calculus. So, integral calculus, you have that very simple identity, which is what we have done to solve that particular case. So, let's call it 4. So, if we simplify this expression 4, making dA over area the subject, we have dA over A is equals to dA over A is equals to dV over V minus dC over C. Let's call that expression 5. Now, we have these expressions, and now we can use expression 3 to obtain the expression for velocity dc. So from expression 3, if we divide both sides of that equation by c, we'll have minus b dp over c, or we'll have dc is equals to minus 2v dp over c. So let's call that expression 6. So if we substitute this expression 6 into expression 5, if we substitute expression 6 into expression 5, what do we get? Very simple. What do we obtain? So we have dA over A is equals to dV over V minus, putting this value 2V dP over C, it becomes plus 2V dP over C squared. Let's call it expression 7. And so if we factor out VDP, factoring out VDP, we have dA over A is equals to VDP into dV, V times VDP plus 2 over C squared. So we just factored out VDP. So when you factor it out, so if you cancel this, you multiply this out, you get that bracket. That will cancel that, that will multiply that, you get that particular expression there. So we have that dA over A is equals to VDP into dV, V squared dP plus 2C squared. This is a very important expression relating area. It relates area to the specific volume, to pressure, and the velocity. It relates area as a function of specific volume, pressure, and area. Pressure and velocity, not area. So this expression relates area, change in area, for the flow to the specific volume, pressure, and the velocity. And that's very important. Now, for a small pressure wave in a fluid, in fluid dynamics, for a small pressure wave, call that velocity of sound. The velocity, which is the velocity of sound, A squared is equals minus V squared then P del V as constant. And remember, this is under constant entropy. And remember, when we are deriving expressions here from these thermodynamic state functions, we are assumed as entropic conditions. So we can plug in this expression for this small pressure wave into that expression there. Let's call this expression 7 so that we don't get mixed up. Let's call that 8. So if you substitute expression 8 into 7, what do we get? We'll get dA over A is equals to V dP into minus 2 minus 1 over A squared plus 2 over C squared. If we rearrange this, then dA over A is equals to V dP into 2 over C squared minus 1 over A squared. Very important expression here. Let's call that expression 9. So we can interpret this expression 9. Remember, it relates the velocity of the fluid to that of sound. So we can interpret this expression in a raw form as it is. And let us look at the case of a nozzle. That's where we have accelerated flow. That's in the case of a nozzle. The case of a nozzle, accelerated flow, there's decrease in pressure. There's decrease in pressure. And of course, the increase in velocity. So if there's decrease in pressure, then when C, velocity of the fluid, is greater than that of the sound, the flow, then what are we having here? dA will be positive. What does that mean? It means that the final volume, the final area is greater than the initial area. So what do we have? We have divergence of the duct. Therefore, divergence of duct. And when C is less than A, dA will be negative. Again, final area will be less than the initial area, so we have convergence of the duct. Now, in the case of decelerated flow, like you'll find in a diffuser, when you have C is greater than A, C is greater than A, then dA will be negative. And you can interpret it as we have already interpreted above. And when C is greater than A, D is less than A, dA will be positive. What about in the case of constant velocity? In the case of constant velocity, remember for decelerated flow, the velocity, the pressure is increases. It's greater than 0. It's positive. In the case of the nozzle, the pressure drops. In the case of the diffuser, the pressure increases. In the case of constant velocity, dP is 0. And therefore, in this particular case, C, whether C is less than A, whether it is equal to A, or whether it is greater than A, dA will simply be 0. Let's have a schematic illustration of these processes of acceleration, deceleration, and constant volume. Let's have a schematic. So let's look at this. We'll have our throat there. In the case of accelerated flow, accelerated flow, What are we having here? C less than A, this region C greater than A, subsonic to sonic, and of course here C is equals to A. And in the case of decelerated flow, let's remember we are talking about a nozzle. Here we're talking about a diffuser. Again, we can represent this schematically. This is the throat. Let me write it nicely here. This is the nozzle. This is our nozzle. This is the throat. Again, we can have a schematic. C is equals to A. So here we have C greater than A, C less than A. And we have already discussed the aspects. There are various aspects. In the case of constant velocity, we have particular reference to a Venturi. Here we have again a schematic, this is just a schematic, so they are not accurate diagrams. So if we have C increase, P increasing, or P falling, C increases, P increasing, C falling. So in this particular case, you cannot have a sonic flow. You cannot have a sonic flow. You accelerate, decelerate it. So you cannot have a sonic flow. So again, this is our throat. A throat, flow, and we have our flow. So it's very important, very, very important for us to know the behavior of flow in this duct, and you will need to have a throat in these particular cases for you to experience those transitions from subsonic to sonic flows and so forth. So let's stop at this particular point. We are continuing with these lectures.